Hi, welcome to the Apache Druid Notebooks. I'm Sergio Farragut. I'm a developer advocate here at Imply, and this is a video that's a continuation to the other Apache Druid Notebooks on partitioning. In this video, we're going to talk about the pruning aspect of it. So we've mentioned it in a few of the other videos, but now we're going to dig a little deeper and demo what partitioning looks like for each, what pruning looks like in each of the partitioning schemes. Let's get started. So let's start by defining pruning in general. Pruning is the process of removing the number of segments that you need to read in order to resolve a particular query. So we start with the broker, and the broker's knowledge of all of the available and announced segments. Queries arrive at the broker potentially with a specific time interval and filtering on partitioning dimensions. And so the broker knows about all of the time segments that it owns and all of the segments that it owns within each time segment. When a query arrives with a time interval filter, it selects the particular time chunk to read from, and by using the filter on partitioning dimensions, we can further filter and select a subset of the partitions to read from in those partitions, whether it's one partition or a few. So let's look at each of the partitioning strategies and see how they behave. So first, let's do dynamic partitioning. So with dynamic partitioning, the time interval can effectively be used to prune on time, right? So you will be able to select a particular time chunk to read from. But given that it's dynamic, that means that the partitions are not ordered in any way, and all queries will always require that we read all partitions within the time chunk. It still uses the segment indexes that are inside each of the segments to filter and quickly scan those segments. So the queries are still efficient, but there's no real secondary partition pruning going on here. We will always read all of the segments in the corresponding time chunks. So let's do a demo of this. First, there's a demo setup where we have a table, the same table, the Wikipedia data, partitioned in different ways, dynamic, hashed, ranged, and we even created an example for constant time, where time is not mapped to a primary partitioning on time. So there's only secondary partitioning. So let's dig into dynamic first. Before, let's talk about the setup. I've turned metrics on for the historical. So I'm using the logging emitter, and I'm looking specifically for the query segment time metric. So that's what I'll be displaying here in the log output as we do each of the queries, so we can see which segments are involved in each of the queries. So let's try the first one. So the first one is Wikipedia Dynamic. Let's look at the segments. We see that the time dimension shows a single time segment for June 27th through June 28th, and that the shard type is numbered. This is what results out of dynamic partitioning. This just means that each partition is split when we reach a number of rows, so the data is not organized in any particular way. So let's take a look at what happens when we query this data. So let's set up a query on Wikipedia Dynamic. Let's make this query a little more interesting. Let's put the page on this. Let's look for the most popular pages within a channel, right? So we're filtering on a given channel. This is the English Wikipedia. We group by channel and page. We order by the count descending to get the most popular pages within the channel. So there's the result. Now, a little something about how the queries are going to work here. With the log, I need to run the queries multiple times in order to get the log to fill up enough to flush and actually output something to the file. So that's why you see me running it so many times. I'll edit that part out in the other demos, but I just wanted to explain that. So we see here that for this query, we have all four partitions, right? We see the ID is the same except for that last part where it shows the partition number. The first partition doesn't have one, but then we see 1, 2, and 3. So we're getting all four partitions of that time chunk for any query that we do on the Wikipedia dynamic table. let's go now to hash partitioning. So with hash partitioning, things change a bit, right? We now have some order in the data. So you'll see here that each value of the partitioning dimension will fall into a different secondary partition, right? They don't have any particular order. We see A and B and C are all just spread across the different partitions, and that's sort of what happens with hash partitioning. They get sort of randomized into which partition they fall into. So with taking that into account, let's see how pruning works. So as before, the time dimension will select the time chunk, but if we do a filter on the partition dimension, let's say on dimension 1 equal to E, we will be able to select a particular partition within the time chunk, right? The one that contains the value E. The query engine will take the filter condition, because it's an equality, convert it into a hash, and translate that into the partition that it needs. Now, if we do an inequality here, let's say less than equal, given that the partitions don't have any order to them, we just won't know which ones to read, right? So we'll need to read them all. Okay, so let's bring in the demo environment again and test this out. So now we're going to look at Wikipedia hashed. It has 4 segments. Let's take a look at them. Again, same time chunk. It's June 27th. We see the shard type is hashed and that it's hashed on channel. We know this means that if we have an equality condition on channel, we'll be able to select a single subpartition to read from, and that's sort of the goal, right? But with other inequalities, it'll behave different. And now let's see it in action. So let's change the same query to the Wikipedia hashed table, run it, and we see now in the result that it's looking at a single partition. If we change it now to an inequality, less than the English Wikipedia channel, and rerun that query again, and now we see that it brings up all partitions. Okay, so let's talk about range partitioning now. So with range partitioning, the data is even further organized, right? So we'll see that in this example we have dimension 1, which is a single character column, and we see that its subpartitions have boundaries, right? The first one is up to the value C but not including it. The second one includes the value C and up to E. The third one includes E and up to G, and anything greater than G is in the fourth one. So now if we filter on this using the partition dimension, let's say dimension 1 is equal to E, we can find a single partition that corresponds to that, right? And so that would be the third partition. If we now do an inequality, we can actually subpartition, select a subset of the partitions as well. So if we use less than equal to E, we'll select the one that includes E and the ones that are before it, right? And if we use dimension 1 greater than E, we can also subselect a subset of the partitions, right? So in this case, we would select the one that includes E, because it includes E and other values, and the next one that includes all greater values. So you see that with range partitioning, there's a lot more use cases that are applicable. So let's bring in the demo. So we see that the range partition table has 3 partitions. It's showing a shard type of range, and we can see in the shard spec the actual boundary conditions. In this case, we partitioned it not just on channel, but on channel and page. That means that the English Wikipedia channel appears in both the first partition and the second partition. And you'll see this will have an interesting side effect when we query it. But the boundaries are now based on both dimensions. The data is sorted on both dimensions, and the boundary conditions are created using values from both dimensions. So let's query it and see how this behaves. And same query again. So now we're going to do Wikipedia ranged, and let's do an equality first. So let's set it to channel equal to English Wikipedia first, and do the same query here. And let's see what the resulting partitions look like. So the partitions are just the two partitions, right? Because it's an equality on the English Wikipedia, but we saw that the English Wikipedia is in two different partitions. Now, if we use an inequality here, we use less than equal, we'll still see the same two partitions, right? Because in this case, the values less than English Wikipedia are in the first partition. So now if we add another equality, right? If we remember, it's partitioned on channel and page. So if we look for a specific value of page, we'll be able, or a specific value of both channel and page, we'll be able to select a single partition. Oh, I messed up the where clause there. Let me fix that. Let's remove that other condition, add the and let's try that again. Okay, so now we get the single value. That's what we expected, and we see it reads from a single partition. So again, if you're filtering on equalities with all of the partitioning dimensions, you will get a single partition either in hashed or range partitioning. So now let's talk about the special case. This special case is where you have a data source loaded with a constant time. And this means that you're not mapping the time dimension to an input field. You're just setting it to a constant value, which means we'll have a single time chunk where all of the partitions will exist. So subpartitioning becomes important here in order to optimize queries. We no longer have the time interval as a filtering possibility, but we can filter on the partitioning dimensions and still select a subset of the partitions for a given query. So let's see what happens with each of the partitioning types. With dynamic partitioning, we'll have to read all of them, so that's probably not a good choice. With hash partitioning, if we have equality conditions on the partitioning dimensions, we'll be able to select a single partition, so that's probably a good choice. If with ranged partitioning, if we have equality conditions, we may get one or a few partitions to read from, depending on the partition ranges. And with range partitioning, we can also service inequality conditions and potentially still reduce the number of partitions that we need to read from. Right? So ranged is good if you need inequalities. Hashed may be better if it's all equalities because it guarantees like a single partition. But one more thing to take into account is that in this special case, there is a maximum number of subpartitions that can exist within a time chunk. And it's a 2-byte integer, so that limit is 32,768 partitions. So anyway, take that into account when you run into this use case. So now let's close by talking about how pruning helps. So with let's say we have a set of historical threads, right? So that's our capacity for processing queries. And if we're processing a query that uses a set of 4 partitions, let's say it's not pruning at all, that means that we'll be able to process those in parallel, right? We'll assign those to each of the threads and be able to resolve the query in parallel by itself in, let's say, 100 milliseconds, right? If each of the segments are the same size and they each take 100 milliseconds to process, the total time is 100 milliseconds. Now, what happens if we add concurrency? So with more queries, and if they are all behaving the same way, so no pruning, that means that the queries are going to get queued up, right? We'll see, each of the threads get assigned one of the partitions, and assuming the query first gets processed first, the other one's going to get queued up behind the others, and therefore the response times are going to vary quite a bit, right? We'll see that each segment is processed in those threads, but that total capacity will require us to process in a total of 400 milliseconds as we wait for the subsequent queries to complete. So anyway, this is not great for concurrency. Now let's take a look at it with pruning. So if we're just picking one segment, so we have successful pruning down to one segment, we'll be only using one thread, and the total time for that single query won't change, right? It'll still be 100 milliseconds. But now when we bring concurrency in, the story is very different. Each of the queries requires a single segment, and we have multiple threads to process them, so we can process more queries concurrently, and now all of these queries can finish in 100 milliseconds concurrently. So, in summary, partition pruning helps because it uses less resources to process each query, and with more resources available, other requests can be processed at the same time. So, the overall conclusion here is that by taking advantage of pruning, you can achieve higher concurrency using the same resources. Thanks for watching. Please like and subscribe, and or comment below. I'd love to make this a conversation.